In the previous video, we talked about the basics of creating and managing two-dimensional graphs, right, in Matlab. This time, in this video, we're going to talk about the so-called special purpose plots, right? 2D plots. So how do we actually create those kind of special purpose plots? What does it mean by special purpose plots, right? For example, sometimes we want to make log-log plots. We don't want the scale of the linear or horizontal or vertical axis to be linear. We want them to be log scaled, right? If you have done some kind of signal processing, one of those plots is called a, for example, if you want to plot the gain of a particular filter or something, then it might be a log-log plot. The horizontal and the vertical axis might be logged axes, right? Suppose the horizontal axis, let's call it, that's the frequency, let's call it OM, that's frequency, equals to log space. So -1 to 1 with 200 points, right? That's going to be our horizontal axis. But it's not link space, right? We looked at the link space quite extensively, right? But this is probably the first time we use log space. In a previous video, we also introduced the log space, right? When we talked about the operations of vectors, vector operations. In that video, we talked about the link space and vector space, right? But this is probably the first time we're using log space to actually create a horizontal axis. And then the h, let's say h represents the gain of the filter or something. One dot divide, sqrt. 1 subtract om dot hat 2, right? That's the square of the frequency, and then dot hat 2 plus 2 times 0.05 times om, right? And then dot hat 2. That's more like the gain of the filter, right? And then t, that's like the angle, phase angle, ATN2. If you haven't used the ATN2, it's a quite a useful function. If you know ATAN, that's the antitangent, right? Arctangent. What exactly is ATN2, right? So what exactly is arctangent 2? Arctangent 2 is going to take y and x, right? So it's going to determine what's going to be the quadrant of the angle, right? So if you just use the arctangent or ATAN, that's not going to determine the quadrant for you, right? But ATN2 is going to determine the quadrant based upon the signs of x and y, right? So it gives you sort of it's more like a bitter ATN function, right? And then y is going to be 2 times 0.05 times om, and x is going to be 1 subtract om dot hat square, right? And then times, we're going to convert it into degrees instead of radian divided by pi, right? That's going to be our t. And then let's how we're going to do that. We're gonna create a new figure. Let's call it figure 3. We're gonna create a new figure, figure 3, right? And then, well, how many subplots? 1, 2, 3. Let's just use 3 subplots. 1 row, 3 columns in the first subplot, and then we're gonna plot a log-log between omega, that's the frequency, om, and h. So how do we actually make this kind of plot, right? There is a special kind of function that's called log-log provided by Matlab, right? So help log-log. So log-log scale plot, right? So it's telling you it is same as plot, except that logarithmic scales are used for both x and y axis, for both x and y axis, right? So both x and y axis are going to be log scale, right? So let's just log. So the usage of the log-log function is kind of similar, right? Horizontal and vertical axis, right? It's kind of similar to a plot function, except that the name has changed to log-log, right? So let's give it a run and see. Let's hold down Control key and press Enter. Right. It's more like a narrow band filter or something, right? So it's actually have a peak that's close to like a 1 hertz, right? and then um, this is just for the gain, for the h, for the amplitude, right? For the amplitude of the field, right? What about t, right? Usually the t is in terms of angles, but usually we want to plot the angles in a linear scale. So we want the vertical axis to be a linear scale, right? But the frequency, the horizontal axis, we still want it to be like a log scale. So how can we actually do that? So log is gonna give us the log scale for both horizontal and the vertical axis, right? So we have to use a different function. So plot 1, 3, 2, right? And then what's the name of the function, right? So it's called SemiLogX. SemiLogX, right? So semilog scale plot x is the same as plot, except that the logarithmic scale is used for the x-axis. So the frequency axis can still be logged, right? But the vertical axis is going to be linear. Because this is called semilog x, so it's going to log the horizontal axis, the x-axis. But if you want to sort of log the y-axis, you have semilog y here, right? And log is going to log both axes, right? So let's use semilog x. OM is going to be the horizontal axis, right? And then the vertical axis is going to be t, right? Let's execute this section of the code. So now that's the horizontal axis. So it goes from 0 to 180 degrees, and it has a switch point that's close to 1 Hz. That's called SemiLogX, right? And suppose we want to sort of plot these two figures together. So how do we actually reconcile the axes, right? Because for this particular subplot, the y is in the log scale, but for this particular subplot, the y is actually linear scale, right? So how do we actually plot both of them together onto the same subplot? There's another function that's called plot yy. Plot yy. So graphs with y tick labeled on the left and right. So it allows you to actually use different kinds of y-axes, right? And then it also allows you to actually specify what kind of the scaling. Is it going to be linear or is it going to be log, right? Log scale, that kind of thing, right? So as a string. So let's use plot yy. So for this plot yy, we're going to plot two curves, OM and H. That's going to be our first curve, right? And this is for the y-axis. It has to be a log, right? For both horizontal and the vertical axis, they have to be logged. And then the second curve we want to plot is OM and T, right? And then we have to specify the scale. So for the first curve, it's going to be log curve, right? And then for second curve, it's going to be semi-log x curve, right? And then let's if we just use plot yy, then it's not going to return. It doesn't have any kind of output, right? But let's return some kind of output. Let's return some kind of output, right? So just like the plot function that can return a handle to the plot, any of those plot functions, log, semilog x, semilog y, plot yy, all of them can return handles to the plots, right? But this time we're going to return more than just a simple handle, right? We're going to return three things, ax, h1, and h2 equals to this thing. So what does it mean? Right? So this function is going to create what? It's going to create two curves, right? OMH is going to be a curve. OMT is going to be another curve. These two curves actually have handles, and those handles are stored inside of h1 and h2. Those are the curve handles, right? It's not exactly figure handle, but the curve handles, right? And then don't forget, we also have an axis that's surrounding these two curves, right? And the properties of that axis, the handles to the axis, is going to be stored inside of this AX, right? So you can think of AX as an axis handle, right? So let's just run it. Let's just run it. And the reason that we want to sort of get those handles is because later on we want to specify its properties, right? So now you've got like two different curves that's plotted on the same subplot, right? One of them is actually, both of them have log scale for the x-axis, but one of them have log scale for y-axis. The other one actually has linear scale for the y-axis, right? So now let's take a look at how we can actually use those properties, right? We can use how we can actually use those handles. Um, so let's try to use the axis. Let's try to use the axis handle. If we do a size x, ax size ax, you're gonna see it's actually two elements. So ax is not just a scalar; it's actually a two-element vector. So you've got ax1 and ax2, right? So what does it mean, right? Because the reason that it's got like two elements inside of it is because you actually have two sets of axes, right? A linear axis and then a vertical, an axis with a log y coordinate, and then an axis with linear y coordinates, right? So suppose we want to change the color, right? Set ax1. Want to change the y color. Let's change red, and then set 2 y color. Let's change it to B, right? Let's just evaluate it. So now you can sort of see the color has changed, right? The color is changed. The reason is because we specified the y color, right? So it's going to change the color the color of the y-axis, right? And the first one is changed to red, right? The first one is associated with the first curve, so it's going to be changed to red. And then the second one is going to be changed to blue, and it's associated with the second curve, which is actually the semilog. So it's going to be the linear curve, right? So that's just for changing the property of the axis. Here we have actually did like two commands, right, to change the axis. An alternative way is just to use one command, set ax, right? And then the property is, so if we, because ax is a vector with two elements, right? So all the properties we have to specify has to be encapsulated in cell arrays. So the property we're going to change is y color, right? In principle, we should type y color, right? So for the two axis property, for the two elements in the axis vector, we want to change y color, right? But if it's actually a repetition, if you just want to change the y colors through all the elements of the axis, then you can just specify 1. And then for the value part, you have to specify the red and the blue separately inside of one cell array, right? So if you run this line of code, it's going to give you exactly the same effect, right? Oh, so it's telling me it's got a axis mismatch, size mismatch. So maybe this y color is cannot be neglected, right? Let me try to rerun it. Or is it? I suspect it's not really the reason. Okay, so now it's working, but for some reason it's not. It's changed to the wrong thing. Oh. Maybe it's a semicolon here. Yeah. Okay, so that looks right. So what I was saying is still you can just use like one property name if you want to change the property name for both the accesses, right? And then to separate the different elements in the second theory, for the value theory, you have to use a semicolon to actually do that. So red is going to be assigned to the y color of the first axis, first element of the axis vector, and blue is going to be assigned to the y color of the second element of the ax vector. Right. So this is actually changing the properties of the axis. But suppose you want to change the properties of the curve. Right. So this time you can use h1 and h2 now. That's the properties of the curves, right? So set h1. So color, let's change it to red, right? And then set h2 color, let's change it to B, right? And then set h1 line width. The width of the line, let's change it to like 2, make it thicker, and then set h2 line width. Let's also change it to 2, right? Let's just execute these 4 lines of code. Right, so the lines are thicker, right? And some other decorations involves putting a box around the plot, right? If you want to put a box around the plot that you have just made, you can use another function that's called box on. So if you execute this line of code, you're gonna see a black box around the curve, right? If the axes are kind of in a different color, then the color of the axis are gonna take precedence, right? It's gonna draw the color of the axis, right? But otherwise, it's gonna just put a black line box around the figure that you just made, right? And another kind of useful option, especially one if you are actually looking at this kind of quantitative plots, right? You want to sort of discover all the values, that kind of thing. From you want to sort of read, you want to be able to actually read the values of the curves, every point on the curves. It might be a good idea to put the grid on. That's another command. Grid on. Grid on is going to turn on the grids, which is going to make it easier for you to actually read the y values for each of the points on this particular plot, right? And then if you want to sort of, so if the grid density is not enough for you, you want to make the grid denser, and there's another command that's called grid minor. Then it's going to plot not just the skeleton grid, but also all the minor grids. Oh, so grid minor on, or minor on, or minor off. Oh, so it's this is weird. So grid minor is more like a toggle, right? So I see what's actually happening now. So for this particular version of the Matlab, grid minor is actually automatically turned on, right? So by calling grid minor again, I actually turn it off. So if I do grid minor again, it's gonna toggle the minor grids off. It's just gonna leave the skeleton grid. But if I do grid minor again, then it's gonna draw all the minor grids. So the minor grids is turned on by default, I guess. So depending upon your settings of your Matlab, you can try it out, right? So if you want to have more grids. So these are some of the capabilities provided by Matlab, right? All the figures are kind of a publication quality. You can sort of include any of those kind of figures in your publications. So for now, all the plots we have been making are just made up of points and lines connecting those points, right? Let's look at some other special purpose plots. These are called stairs Stairs, stem, bar, and pi. Right. So stairs, let's create another figure. Let's call it figure 4. Right. Let's call it figure 4. And then subplot. 1 row, 3 columns. First one. Right. We're still gonna use this kind of filter example that we have created. Right. OM and H. Let's make a plot of it. Let's make a stair plot. Let's make a stair plot. So stairs is a Matlab command, right? You can use it just like a plot function, right? So let's hold down the Control key and press Enter. So for some reason it's not really. So if I blow it up, it might be easier to see, right? So the reason that you don't see the stairs is because the horizontal axis, the interval, the spacing of the horizontal axis is kind of too small, so you won't be able to see it. But you can sort of see the difference now. So every point is just gonna draw a flat horizontal line at the location of every point. So it's not gonna do a linear connection between neighboring points, right? So what's gonna be used for connecting is just gonna be this kind of horizontal line and vertical line, right? So it gives you a sense of looks like a stairs. Right, looks like stairs, and that's called the stair plots, and it has utilities in some special kinds of applications, right? And then subplot, 1 row, 3rd column, 3 column, and a second plot, right? We're gonna use stem, OM and H, right? Evaluate selection. So that's gonna give you a different sense of plot, a different kind of a plot, right? Again, let's zoom in because it's kind of difficult to see, right? So that's called a stem plot, right? So it's gonna be lots of vertical lines, right? The horizontal vertical, every line is defined by just 2 points, 1 point on the top, 1 point at the bottom. The bottom point is always located at y equal to 0, but the top point is going to be located at whatever y value provided by the function, provided by h, by the y value here, right? And then at that second point, the top point, there's going to be a circle, right? Matlab is going to automatically draw a circle, right? The circle is going to have a center at the location of the y coordinate of the second point, of the top point, basically, right? And that's called a stem point. You don't see the lines connecting all the circles, right? You only see those vertical lines, and that's called a stem. And then subplot 1, 3, 3. We're gonna do the bar plots. We're gonna do the bars, right? Bar, OM, H. So if we just use the bar function like that, it's just gonna create something like looks how do I say? It's not so good looking, right? So how exactly do we want to use the bar function, right? How do we actually want to use the bar function? Let's take a look at the help page, right? Help bar. So by default, it's just going to draw the columns of x and y, basically, right? It's more or less like the stem function. Except that it's not going to be a circle on top of a stick. It's going to be a vertical bar, a vertical rectangle, right? And then it's got some specifications here, right? The third input is called the width, right? So it's going to specify the width of the bar. So if the value of width is larger than 1, then it's going to producing overlap bars. The default value is width equals to 0.6, right? And then it's got another option after the width, which is called either grouped or stacked or line spec, right? Um, it's got different kinds of utilities, right? And we can look at them in just a little bit, right? But let's try to sort of say, let's use the width function 0.6. Uh, let's give width 0.6, and then let's give the color black, right? And then oh, it's I entered at the wrong location of the code, so let me cut it and then paste it here, right? So for some reason it's not displaying correctly. For some reason, I don't exactly know, right? But it works fine on my local computer. But for this particular version of Matlab, uh, maybe it's a problem with the access, maybe. I don't exactly know, right? Um, maybe I should try another plot with linear scale. Let me try to do another example. Right. COF. COF is a command for clean up this particular plot, this particular figure, basically. So if I run COF, then you're gonna see every subplot on this particular figure has disappeared, right? So it gives me a clean slate for me to actually make new plots, right? And let's do something that's relatively simple. So x goes from 1 to 10, right? And then y equals to, let's just do a random matrix with 10 rows, 10 columns, 10 rows and 2 columns, right? 10 rows and 2 columns. And then let's just do a bar, x and y. And then let's do a stacked. And then let's see what's gonna happen, right? Let's plot the first column without the stacked first. Let's just use the simplest case, right? Let me run this piece of code. So that's like 10 random numbers, right? We're just plotting the first column of y. So the vertical axis are going to be the first column of the y, right? And then if we want to try to adjust the width of it, let's give it like a point. So by the default width is 0.8, right? Suppose we increase it to 0.9. Oh, sorry, I put it in at the wrong location. 0.9, right? And re-execute this line of code. You can sort of see the gap between neighboring columns are going to become smaller, right? And then if you actually use a width that's exactly 1, you won't be able to, so let's just evaluate it. Right, you won't be able to see any gaps between neighboring columns. So the width parameter allows you to adjust the column width. Let's change it back to 0.6, right? So make it a relatively thinner, right? So there's some more gaps between neighboring columns, right? And then that's just plotting the first column, right? But don't forget y actually has 2 columns, right? And that's where the last option is going to become sort of interesting, right? Suppose we do stacked and then get rid of the index. So we're going to use the 2 columns of y instead of just one of those columns. We're going to use the 2 columns, right? And then let's just run it. So now you sort of see the effect of stacked, right? So the blue columns are still the values, still indicate the height of the blue columns still indicates the value of the first column of y, right? Bunch of random numbers. But the height of those yellow columns are gonna be the value of the second column of the y matrix, right? That's called a stacked. So the blue column and the yellow column are gonna be on top of each other, right? The yellow column are gonna be on top of blue columns, right? And don't forget, there's also another option that's called grouped, right? Suppose you run it as grouped. So it's going to look like that. So the yellow columns are not going to be positioned on top of the blue columns, but it's going to be next to it, right? But with a smaller gap, right? So they are going to be separated into groups, and each group actually has one blue column and one yellow column, right? So that's the first column. That's the first row of the Y matrix. It's got two columns. That's the second row of my Y matrix. It's got two columns, right? And then that's how stacked and grouped are gonna work out, right? And then, so this is sort of the two-dimensional bars, right? In some of those applications, you might have seen three-dimensional bars, right? And Matlab also allows you to plot three-dimensional bars. It's called bar 3, right? Suppose we do that. Bar 3 is going to give you a three-dimensional bar plot, right? And you can actually rotate it. So in principle, this is supposed to be discussed in three-dimensional plots, right? But because we're talking about bar plots, so let's just cover this kind of effect in this particular video, right? And sometimes you see horizontal plots, right? Horizontal bar plots. And Matlab also provides that kind of capability. It's called bar 3H or bar H3, bar 3H, right? So bar 3 is going to be three-dimensional bar, but those are vertical bars. But if you do bar 3H, it's going to be horizontal bars. That's horizontal bars, right? So if you want to rotate it, you have to sort of click on this button here, and then you can rotate it, right? That's horizontal bars. Okay. So if you get rid of the 3 here, bar H, that's just going to be two-dimensional horizontal bars, right? So that's bar plots. So now let's talk about pie plots. So pie charts, right? Let's try to come up with some kind of fake data. So D equals to 39, 10, and then 1, for example, right? Doesn't matter how. And then let's try to make some subplots. So let's make 8 subplots, and we're going to organize them into like a 2-row 4 columns. 2-row 4 column, and then in the first subplot we're going to just do a simple pie plot, right? It's just like that. Right? So let's take a look at the effect. So that's what the pie plot is going to create, right? So what does it mean, right? 78%, 2%, 20%. What exactly does it mean, right? So it's plotting this vector D, right? It's plotting this vector D, and this D actually has 3 numbers in it, right? So this pie function is going to create is a pie chart, right? And then it's going to fill up it's going to cut the pie chart into different portions, right? The biggest portion, that's 78%, actually corresponding to the number 39. The second one is what? The second one is like 20%. 20% corresponds to 10. And the last one is 1%, is 2%, right? 2% corresponds to the number 1, right? So what's how so it's gonna do the pi function is gonna do a summation for all the elements inside of D, and then use that summation as the denominator, and then use each of the individual number inside of this vector to divide that denominator as a numerator, and then get the proportion, and then it's just gonna cut the pi according to that proportion, right? So if you don't believe me, 39 plus 10 plus 1, that's 50, exactly 50, right? So 39 divided by 50, that's 78%, right? So 78%, that's this blue chunk. This blue chunk corresponds to this 39, right? And then 10 divided by 50, that's like 20%, right? And then 1 divided by 50, that's like 2%, right? So that's what pie chart is gonna do. And then let's look at some capabilities, right? So subplot 2 row 4 columns in the second subplot, but this time we're gonna make a 3-dimensional pie chart, right? But it's called pi 3. That's gonna be a 3-dimensional pie chart. Right? That's what the 3-dimensional pie chart actually looks like, right? If you want to rotate them, it's gonna change its orientation, right? That's pi. That's 3-dimensional pie, right? And then let's look at another effect of pi plot. That's called suppose sometimes maybe you might have seen that you can actually shift some of the chunks away from the radius of the pi, right? Sometimes, right? And Matlab also provides this kind of capability. It's called pi. The data we want to plot is D, right? And then we're gonna have 3 numbers, right? 3 numbers, 1, 1, 0. So this time we're actually plotting the with this particular vector. What does it mean, right? So if you haven't actually used the pi function before, let's look at the second vector is called explode. It is used to specify the slices that should be pulled out from the pi. So the vector explode must be the same size as x. In our case, is D, right? D has like 3 numbers in it. So explode should be 3 numbers vector, a 3-number vector, right? The slices where explode is non-zero will be pulled out. So which means what? Which means the first chunk and the second chunk are going to be pulled out. The first chunk corresponding to this thing, 39, that's 78%, right? And then 10, that's like 20%, right? So, and then the last chunk, which is 2%, is not going to be pulled out. So if we evaluate it, right? So you can sort of see that this chunk and this chunk are being pulled out, right? It's called explosion. That's one of those effects, right? And of course, pi 3 also supports this kind of explosion input, right? But this time it's let's use 4 pi 3 D 1 1 0, right? Right. That's 3-dimensional pi um, with the explosion, right? With the explosion. The color that you actually have, the color that you have that's being used for making those plots are kind of default color, right? Suppose you don't want to use the default color. You want to use a different color, right? If you want to use a different color, you can what you can do is to use another Matlab function called color map. And the color map function provides a set of default color maps that you can actually use, right? um, color lookup table. Color lookup table. Right. Suppose we want to change the colors to a different set of colors, right? Subplot 2, 4, 5, right? And then let's do pi d 1, 1, 0, but this time let's change the color map to something that's called cool. So cool is one of those built-in color maps provided by Matlab, right? So let's see what's going to be the effect. Right. So now it's going to change the color map into this kind of color, right? Whether it's what you want it or not depends, right? You can. There's a bunch of selections, right? Uh, there's a bunch of default color maps that's actually built into the built into Matlab. You can select, right? So you can actually use this color map function. So if you want to find out what are the built-in default color maps, you can try to look at the reference page for color map, right? Or just by googling color map default color map in Matlab or that kind of thing. Then it's gonna give you a list of those default color maps, right? So I'm not gonna. So I will skip doing that in this particular video, right? So of course you can. So of course you can sort of repeat what we have done so far. 2, 5, 4, 6, right? 2, 4, 6, pi 3, d 1, 1, 0, but also with the color map. Let's change the cool, right? And then the last thing I want to demonstrate for the pie plot is legends, right? Legends. So so how do you actually put those legends onto the different chunks of the pie, right? Suppose all those numbers inside the D vector is sort of the spending of a particular company on different sections, on different categories, right? So let's try to convert the D into a proportion vector. So P equals to D divide sum of D, right? And then say times 100 to convert it to like percent or something, right? And then let's define a few strings. So A is going to be the string that we want to use for the legends, operational with a space behind it, and then num to str p the first element. That's operational, and then with a percentage sign, right? So that's a string. We're concatenating these words together into a string, but because p1 is a number, in order to concatenate those numbers with the strings, we have to convert the number to a string first by using num to str. Right, we have been using this particular function quite extensively in previous videos. So, and then b is equal to initial investment or something, right? Num to str p the second element. Oh, it's not. And then percent. And then c equals to R&D, research and development, num to str p of third elements, right? And then percent. Right. And now we can sort of do subplot. Now we can actually do a pie plot, and then p is what we are plotting, right? And then we want to do some kind of explosion, right, for the first two chunks. And then what's going to be the legend for each of the chunk, right? We're going to use a cell array for grouping together, those three strings that we just constructed, right? And then color map. right? Let's run this particular section of the code. It's kind of small, and it's 247. Sorry, 247. Right. Right. So now we have. So maybe I should just remake the whole thing. Um, right. So now you have those text that's denoting each of the different proportions, right? R and D with a space. Yeah, that looks better, right? And then, of course, this kind of a legend, this kind of a pi legend, is also applicable to the three-dimensional plot, right? So you can do pi 3 p 1 1 0, and then a b c, right? Right. So that's gonna give you this kind of thing. Right. So one of those things that you may have noticed is that every time I change the color map, the new color map is going to be applied to all the different subplots, right? So when did I actually change the color map? I changed the color map on the second row, right? Starting from the fifth subplot, I changed the color map to cool, right? But all the subplots that I have made previously on the first row, subplot 1 to like 4, all of them are going to change to the same color map, right? And this is one of those things about Matlab that's kind of not so satisfactory, right? But people have noticed this particular drawback, right? Suppose you want to apply different kinds of color maps to different subplots, right, in the same figure, right? So how do you actually do that? How do you actually do that, right? There is a quite good third-party function that's called freeze color. It's called freeze color. I won't be able to actually demonstrate how to use this particular function, but let me just go to the website, and it's called freeze colors. It's very easy to use. All you have to do is to actually just type freeze colors for after you have finished making each of the subplots, right? And then you will be able to actually freeze colors, right? So it's actually inside of the Matlab file exchange, so you can actually download it for free, right? So you can sort of see they're actually using different color maps in this different subplots of the same figure, right? And all you have to do is to download this particular file and then put it in your current folder, current working folder, and then you will be able to actually specify different color maps for different subplots.